Okay, so we're starting on another topic, and we're probably going to stick with this one for a couple of days because it is a little bit of a challenge. But I like this one. This is one of my favorite topics as a student because it's a puzzle. You have things that you have to figure out in order to make things work. So I'm going to cut it up into small pieces, as small as we possibly can. So the topic that we're looking at is called integration by substitution. You might also see it called U substitution or the reverse chain rule. So in order to use this, we can do this to do those more kind of complicated integrals, and where you've got functions within functions. So in order to be able to use integration by substitution, you have to be able to write an integral in this format. So you have some function with a function within it, and then times the derivative of the embedded function. So let me show you what that looks like. So this would be an example of a function that we could do that with. So if I had the integral of cosine x squared times 2x dx. So in this situation, my f of x is the cosine function, right? My g of x is the x squared. So the x squared is embedded within the cosine function. And then my derivative of g of x, or g prime of x, is the 2x. Okay, so if we can do that, we can then rewrite this function as cosine u du. So u is my g of x. Okay, so I take my derivative, or my integral here, and the integral of cosine u is sine u. And there's no upper or lower boundaries, so we do have to have our plus c. And then I'm just going to put u back in there. I'm going to put the x squared back in for u. And that's my answer, plus c. So first thing we have to do is we have to have our integral written in the appropriate format. Sorry, my cat's starting early today, you guys. Okay, so integral in the right format. Okay, then we replace g of x with u. That's where the substitution comes in. We take the integral, and then we put back g of x. And it's that easy. It's that easy, y'all. So the reason we can go ahead and replace this du now that this is all written out is within this function, we have a derivative. 2x dx becomes du because 2x is the derivative of u. So we then replace our 2x dx with du. We replace our x squared with u, do our integral, and then put u or g of x back into the function. So let's try one more. All right, so we're going to try one that is just a tiny bit more, no, we're not even going to try one that's a little tiny bit more complicated. We're going to go this easy. So let's take the integral of e to the 3x power. Let's say 3x squared power times 6x dx. So I have my original function, or I have my f of x, e to the 3x squared power. So my f of x, you don't always have to write this down, but it's a good idea as you're working on it to keep track of your function. So my f of x is that e to the x power. Let's call it. My g of x is the 3x squared, because I know how to take an integral of e to the x power. What I don't know how to do is an integral of e to the 3x squared power. So that's where we need to use the substitution. Now, 6x is the derivative of 3x squared. So g prime of x is 6x. Perfect. So I'm going to call g of x u. So in my original function, or my original integral, this is du. And then this is u. So now I can go ahead and rewrite that as e to the u power du. Now I can take that integral, e to the u power, the integral of e to the u power or x power is just e to the u power. And then I'm going to put my u right back in there. Put the g of x right back in for u. And that's it. That's it. That's all you have to do. That's all you have to do. That's it. All right. So let's try one more. Just one more. Okay, so I know that there's been some problems in some of the practice that I gave you that sort of looked like this, where you could take the, where it was just like a polynomial squared. And in that situation, it's real easy to just square that and turn it into, you know, a normal polynomial that you can deal with. But when you have a polynomial to the 5th power, that's a lot of multiplying polynomials out, and that's a lot of extra work that we don't need to do. So if I look at this right here, I have 2x squared plus 4. The derivative of 2x squared plus 4 is just 4x. So I have my f of x, g of x, and my g prime of x. So f of x is 2x, or sorry, my f of x is x to the 5th power. My g of x, let's call this u. I think all these x's get a little confusing. So my f of u is u to the 5th power. My g of x, or my u, is 2x squared plus 4, and my g prime of x is 4x. Okay, so I'm going to rewrite this, substituting u. And this right here is my du, my derivative of u in terms of x. So u to the 5th power, the integral of that would be u to the 6th power over 6. And then I'm going to take my u and substitute it back in there. So that would be 2x squared plus 4 now to the 6th power over 6. And that's it. It's very simple stuff, you guys. So you can do a definite integral with these. Oh, and don't forget our plus c's. Did I do plus c on the last one? No, I didn't do plus c on the last one. There you go. I fixed it. Okay, so you can do a definite integral using these. So let's say we had wanted to do from 0 to 1. Let's make our lives easier. So from 0 to 1. So I would still go ahead and plug in from 0 to 1. So that becomes 2 times 1 squared over 6 plus 4 over 6. And so that's if we plug in a 1. If we plug in a 0, that becomes 0 plus 4 over 6. So this gives me 1/3 plus 4/6 minus 4/6. So that would equal, so that would equal 1/3. So we can do our definite integrals using this rule. It's just one rule that you can use to help you solve. So we're going to look at some more examples like these today, and then we're going to look at on Tuesday some problems that are not automatically set up the way that they need to be, and how you can adjust them to set them up the way that you need them to be in order to solve. And I will also be putting out review for your performance final, because that's going to be coming up very, very soon. And I'll put up a list of topics that you all need to go back and find in your notes and stuff for the final exam. All right, have a great day.